In order to do science, in order to all be on the same page with the same tools, one of the most important things that you've got to get used to doing is using units. Units and understanding units and unit system. What do I mean by that? Let's say I ask you how far it is from Lynchburg to Roanoke. Okay. So, yeah, I'm just thinking how far it is from Lynchburg to Roanoke. Let's just say Lynchburg to Roanoke, and I'm going to approximate. I might get a little wrong, but let's say I want to know how far it is from Lynchburg to Roanoke. You could answer me in many different ways. You could say the answer is 60. You could say the answer is 100. You could say, for that matter, the answer is 1, right? Is it 60? Is it 100? Is it 1? Actually, the correct answer is yes. It is all of those. It is all of those and more. It is also 32.5. I mean, so, and the reason why it is any or in all of these is because we haven't told you what units I'm asking for the distance between Lynchburg and Roanoke, all right? And again, I have it wrong a little bit because it's probably closer to 45 miles, but let's just say Lynchburg to Roanoke is 60 miles. Lynchburg to Roanoke is 100 kilometers. Lynchburg to Roanoke is 1 unit of distance, which is defined by the distance from Lynchburg to Roanoke. Right? Let's just call it the LBROA, or we can just call it franc. We can just name our unit. 1 franc. 1 franc is the distance from Lynchburg to Roanoke. It's 32.5. Maybe it's 32.5 minutes in a fast car. Right? So how far is it from Lynchburg to Roanoke? Yeah, we were implying distance, but I don't know if we said that, and so we can talk about how much time it would take. So as long as we put units, then we can only get one answer. Units are absolutely essential. It is absolutely essential to use units on 100% of your answers in physics. And we have got to understand how to use units, and we've got to understand the unit system. So I just want to take a little bit of time to talk about the units, general unit systems, and the unit systems we'll use in this class. But we have got to use units, miles, kilometers, whatever, defined units, minutes, etc. Another reason to use units. What if I said that the distance from Lynchburg to Roanoke is 35 tons, right? Say, but ton is a weight. It's not a unit of distance. So by adding a unit to it, if I calculate something, if I'm trying to calculate something, you give me some data and I calculate the distance and I get the distance of 35 tons, the fact that I got tons tells me that I made an error in my calculation. So the units can tell you if you are in the right track or on the wrong track, right? So if I tell you it's 35 tons, tons. Oh, what's going on? My pad's not working. Right, then incorrect, right? We know that you can't measure distance in any way as a weight. So you've got to carry units through your calculations in order to make sure that you know that you're doing your calculations correctly. Quantities do we use to measure things? What I mean by that is what are the different units that we use to measure things, right? How do we measure them? Like, for instance, if I want to measure the amount of energy in a snack, right? Calories, or the amount of energy in a moving object, also calories, but we often use joules. The amount of light that's that comes out of a lamp. We might measure the power, which is the units are watts. The quantity that we use is watts. Or horsepower is the power that comes out of a car that we measure typically for something like a car or an engine or a motor or something like that. What quantities do we use to measure things? Really, what units do we use? And what's important here is to look for what's common in all of these units. What do I mean by that? For example, let's say that I say I'm going to measure energy as a joule. You can look up the definition of a joule and you will find that 1 joule is 1 kilogram meters squared per second squared. So what does that mean? Well, it's a little hard to say what that means. to be really careful. But it means that we're taking 1 kilogram. It's the amount of energy it takes to a 1 kilogram mass over a distance of 1 meter in 1 second to a speed of 1 meter per second, if that meant anything. But it's a measure, right? So the point being here, though, that joule can be measured in terms of mass, distance, and time, something that we do to a mass over a distance and time. An easier one to see is the Newton, right? The Newton, N, it's a measure of force, and 1 Newton is 1 kilogram meter per second squared. So it's slightly different than the joule, and it's a very different quantity. It's the amount of force that it takes to accelerate a 1 kilogram mass to an acceleration of 1 meter per second squared, or the amount of force that it takes to change the speed of a 1 kilogram mass by 1 meter per second in a second. So it's that force. And you might ask, like, joules and newtons are not units or measures of quantities that I'm familiar with. I'm familiar with calories and pounds. But the difference between a calorie and a joule is just a unit conversion. And that's what we're going to talk about next, is unit conversions after we talk about units, right? We can convert from calories to joules. What is it, 4.1 something calories per joule? And we can convert from pounds to newtons. 1 newton is 2.2 pounds, 4 points, gosh, I wish I knew these things. But right, those are unit conversions. It's different than what are these units. So I'm just starting with the units which are clean, 1, right, instead of 4.1 and 2.2. And then we can do unit conversions to convert them to units that you're more familiar with. I looked up the conversions since I don't often remember them. These over here are just unit conversions. When I said 2 point something, if you invert 4.184, invert 4.45, you get 2 point something. So I was just doing the conversion the other way around. But anyway, these are what's called unit conversions that we'll talk about next. But first, we just got to talk about the units themselves and what a unit is. Really unique about my units, but if you think of any unit, what is in common, what I'm trying to get at here, is that any unit can be written in terms of a length, a time, and a mass, right? The joule can be written as a kilogram times a meter squared over a second squared. A Newton can be written as a kilogram meter over a second squared, etc. A velocity is a meter per second, and acceleration is a meter per second squared. A momentum is mass times meters per second, right? Is a mass times a distance over a time. So every unit, this is the key here to what quantities do we use to measure things, is that every unit is measured in terms of a mass, a distance, and a time. You give me a unit, I'll give you the equivalent in terms of mass, distance, and time. Right? Again, just to be clear, right? I messed something up there. Anyway, just to be clear, just rewrote them. These are all just units. I'm not talking about actual, anything other than units. That the units used for energy, force, speed, whatever, are written in mass in terms, even though we give them all different names, they're written in terms of mass, distance, and time. Now, I got to be careful that when we add electricity and magnetism, we also have to add charge. That is another what's called fundamental unit that we have to add the concept of charge in order to talk about our units of electric field, magnetic field, etc. But for physics 115, it's just mass. Every unit is mass, distance, and time. So in order to measure everything in terms of mass, distance, and time, we need to have a mass standard and a distance standard and a time standard. In other words, if everything is measured in terms of mass, distance, and time, then we need to just define, here's our standard mass to compare everything to. Here's our standard distance to compare everything to. Here's our standard time. So we have to choose system in order to look at the definition of these. So in physics, we are typically going to default to the metric system. And specifically, we're going to default to what's called the MKS system. So in the metric system, we can measure mass, distance, and time. Let's, for example, as a mass. Whoops, not meter. Well, kilogram, right, is a mass. A distance is a meter. Oh, great. And time is a second. Right? Or we can measure mass as a gram and distance as a centimeter. Time, we typically still use seconds. These three systems, and I wrote them around in a funny way, but these three systems, these three units, if we use kilograms, meters, and seconds, we call that MKS, for meters, kilograms, and second. We call this CGS, right? MKS, CGS. Those are our unit systems. The metric system has subsystems, right? We can talk about the meter, the kilogram, and the second, MKS. Or the centimeter, the gram, and the second, CGS. In the British system, right, the British system, mass is, does anybody know what mass is? Raise your hand. Okay, nobody knows what mass is? Okay, it's the slug. Not the pound, because pound is not mass. Pound is weight. Mass and weight are different from each other. That's super important to understand, that mass is not weight, weight is not mass. Those are different quantities. They're measuring different things. Let's take an aside here. Ask, what is mass? Who knows what mass is? Mass actually has two independent, completely different definitions that it turns out gives us the same quantity. Mass can be measured as the amount of stuff you have. That's simply what mass is. It's the amount of stuff you have, right? You count the number of atoms you have. You count the number of electrons, protons, and neutrons. Or mass can also be a measure of how hard it is to change a body's motion. And a more massive body is harder to speed up and slow down than a less massive body. You know, a car is harder to push down the road than a basketball. And so mass is a quantity that has to do with how hard it is to change a body's motion, or is a quantity that has to do with how much stuff you have. Weight, on the other hand, weight has to do with the gravity as in the physical quantity of the planet pulling things. Weight is the force exerted by gravity on an object. So the weight of a basketball on Earth is going to be different than the weight of a basketball on the moon, because the moon pulls with a smaller gravitational force than the Earth does. The weights are different. But what about the mass? How much stuff do you have? If you are carrying a basketball, how much stuff do you have? You have a certain number of atoms in that basketball. You have the same amount of stuff on the moon. You have the same mass on the moon, but a different weight. The reason why we typically don't differentiate between mass and weight, the reason why a non-scientist often doesn't differentiate between mass and weight on the Earth is because we don't leave the Earth. So a certain mass has an equivalent weight, has a weight, and it doesn't change. So while the mass doesn't change if I go from America to China, the weight doesn't change if I go from America to China. But if I go from America to Mars, the mass doesn't change. But if I go from America to Mars, the weight does change. So there's this confusion that mass and weight are the same thing, but they're not. They're very different things. Okay, we will come back to that in a later chapter. So anyway, back to the British system. The British system distance is, or at least at one point in history, was the foot, and the time, again, is also still the second. Slug foot second. And the British, initially the distance was the length of the king's foot, right? And I think at some point it changed to the yard. But in any case, that's just an example of a different of a different unit system. The mile is a distance in another system, right? The hour is a time in a different unit system. So there's all these different unit systems. But when we go between, for a distance, when I go from meters to centimeters to foot, we know there's a conversion factor because those are all just measuring a length. Okay, so I might have been interrupted. Oh, I know. I was just saying my doorbell rang. So I was just talking about when we're talking about distances, they're just conversion factors. There's 100 centimeters in a meter. There's 3.1 feet in a meter. Right? Kilograms to grams is 1,000 grams in a kilogram. I don't know how many slugs are in a kilogram. You can look that up. Seconds. But there's 3,600 seconds in an hour. If I use the hour instead of the second, right? So if we go along one of these lines, there is a conversion factor to go along the line, right? But each of these quantities is defined independently of the other. A second is defined completely independently of the meter, which is defined independently of the kilogram. So we need to choose a system in order to understand units. We need to choose a system and stick with it. In this class, you can use any system you want. But we are going to default to the MKS system. Meters, kilograms, second. Meters for distances, kilograms for mass, and time, seconds for time. We're going to default to that. And you do not, this is really important, you got to listen to this and hear it. You do not have to use MKS unless the problem asks you to. In other words, you don't have to convert everything to MKS unless the problem asks you to. But if you don't know what you're doing, my suggestion is to convert everything to MKS so we're all on the same page, okay? But if we're talking about a car and a car is going 20 miles an hour down a road and it takes 3 hours, how far does it go? 20 miles an hour times 3 hours is 60 miles. It goes 60 miles. We didn't have to convert to MKS in order to answer that question, how far it goes. If I asked how far does it go in meters, then we could take 60 miles, and we can say, oh, there's 1,609 meters per mile, and so it's 60 times 1,609 meters. Okay, so let's just talk about the definition of the MKS system. So this is where we are right now, is we really just want to talk about how the MKS system is defined, and all the other units are defined from those. In order to understand and use units, you do not need to understand what we're going to talk about now. But I think it's super interesting. It is super interesting that every single unit you could possibly use is a combination of meters, kilograms, and seconds, and charge when we get to electricity. And so, but in order to define our units, in order to know that we're all talking about the same thing, these things have to be defined. These things have to be defined. Everything else is just derived. These three have to be defined. So how do we define them? That is a hard question. It is so hard that we didn't really answer that question, sort of, until last year. For the kilogram, we never defined a kilogram, really. I mean, maybe we did in your estimation, but we didn't really. Okay, so for instance, what is a meter? Definition of a meter. Is it a meter stick that we pull out of the lab? No, that's not the definition, because that meter stick had to be created from some definition of the meter. Right? So there is some standard of the meter. At the meter stick making company, they have a standard length, which is a meter on a machine, and they make all their sticks that length, right? So they're taking a standard. But where did they get that standard from? Who defined that standard, and why do we care? Right? Of course, hopefully it's clear why we care. Somebody has to define the standard. It has to be reusable so that we can do science. So that when somebody makes a measurement in England, that they're going to get the same measurement. So that this whole thing about nature of science and the scientific method, right? If somebody makes a measurement in England, hopefully the same measurement can be made in Australia. Right? Let's say that they're measuring the average height of a koala. Hopefully they're going to get the same, if they use the same set of koalas, they get the same average height in Australia as they do in England, because they're using the same standard of measurement. So that standard has to be set by somebody. And the standard has been set. Right? The meter, I'll just write them all down. Okay, one thing that I think I said earlier, which was incorrect, is that the meter, the kilogram, the second, or the standard for distance, the mass, and the time were not defined in terms of each other. They indeed are defined in terms of each other and another standard. So, for example, The second, let's start at the bottom. The second is defined as the duration of 9,192,631,770 periods of radiation corresponding to transition between two particular energy levels in cesium-133. Okay, don't worry about what that means, but it's a very specific definition that anybody who has the right instrumentation can measure. And so it's something that in nature is known to be incredibly constant, these periods of oscillation between two particular energy levels in a cesium atom, and you just count 9 trillion of them and you got a second. All right, then let's go to the meter. The meter is a length traveled by light in a vacuum in a certain amount of time. So time has to be understood. Now the new standard is we're actually, right, we've got the speed of, so the first standard for the second is how much this cesium atom wiggles up and down. The second standard for the meter is how fast light goes. We know that light is incredibly constant speed. It doesn't change. That's an accepted thing in science. And so you just measure how far it goes, and we use the definition of the second. The mass is a really interesting one, because until last year, really until 2011, but until last year when it became official, the mass was always just a lump of platinum in France. Believe it or not, it was just a lump of platinum in a special vacuum sealed cylinder in France, and everybody had to go to France and put that lump of platinum on a balance and put their mass on a balance in order to get the standard of mass. And of course, nobody actually really did that, but there are a lot of duplicate standards out there, but there's a single lump of platinum in France that is the standard kilogram until they finally said, we need something that is unchangeable, because a lump of platinum is changeable. It changes. Atoms come and go, right? They stick, they degrade, whatever. And so they recently, only in 2019, did they determine a new measurement for mass, and they determined it in terms of what's called the Planck Constant. It's a little bit complicated. I won't spend a lot of time here on that here. So let's say real quick what the kilogram is this Planck Constant, which is a number, times 1 second over 1 meter squared. So in order to find the mass, we need to know what a second is, and we need to know what a meter is. So the mass is defined, so the second is defined in terms of oscillations of the cesium atom. The meter is defined in terms of speed of light and oscillations of the cesium atom. The kilogram is defined in terms of Planck constant, speed of light, and oscillations in the cesium atom. So they do build on each other, but they are unique definitions because they each require another measurement. And this Planck constant, again, we won't talk about that. You can look it up if you're interested, but that is something that has to be measured independently. Okay, so these are the definitions. We have these standards. Now they can be reproduced by anybody who has the instrumentation in their lab. They can be reproduced, and everybody knows what a meter, second, and kilogram is. And so everybody knows what a joule is, what a newton is, whatever unit you want. What unit of speed and acceleration and force and energy and momentum, all those things are now defined. Okay, so bottom line is we need to write all of our units in terms of meters, kilograms, and seconds. We need to know how to get there. So the next question comes as to conversions, right? If I know something in terms of feet or yards, how do I get it to meters? If I know something in terms of kilograms, how do I get it to a British system of slugs, etc.?